Hi friends, we hear the word potential in our everyday life a lot. For example, that sportsman has a lot of potential. Or your parents say you should work hard to realize your potential. Or that's a potential customer or a potential client. So we keep hearing this word potential. But in today's video, we are going to talk about electrostatic potential in physics, which is also known as electric potential or voltage. I'm going to make the concept of electrostatic potential absolutely easy for you. So make sure you watch the video till the end. But before we begin, I just want to say, do check out our website manochaacademy.com and our Android app. Links are given below. Alright guys, are you ready to dive into the world of electrostatic potential? Let's begin. What is electric potential difference? Let's look at its definition. So if you pick up your textbooks, you'll see something like this. Electric potential difference, or also known as voltage, it is the amount of work done. So it is the amount of work done by an external agent, okay, in moving a unit or per unit charge when you're moving the charge from one point to another. So imagine we have 2 points here, point 1 and point 2, and we have picked up a tiny test charge. There's a tiny test charge and it's a positive charge which we are going to label as plus Q naught. Okay, and we are moving this charge from point 1 to point 2. So we are moving it here from 1 to 2. Okay, you're moving the test charge from 1 to 2. Then what does electric potential difference say? The potential difference between these 2 points. Note here, the potential difference between 1 and 2, which I can say is the potential at 2 minus 1, right? So we can say the electric potential difference V2 minus V1. Why am I doing V2 minus V1? Because final minus initial. The test charge is moving from 1 to 2, right? So V2 minus V1, and look at the definition. It is the amount of work done in moving the charge from 1 to 2. Work done by the external agent per unit charge. Per unit charge means you divide it by the amount of charge, and in this case the charge is Q naught. So I'm going to divide it by Q naught. That's it. This is the definition and the formula of electric potential difference, right? Difference means you're comparing 2 points. So V2 minus V1 is work done in moving the charge from 1 to 2 divided by the charge. Is that clear? Now there's one more very important thing here, that can we just quickly move the charge like this? No, because when you do that, then the charge will gain some kinetic energy, right? But we want to move it very, very, very slowly. We want to move it very slowly. So we should add something over here, that when the charge is moved very, very slowly, so that there is no change in kinetic energy and all the work done creates this electric potential difference, or you can think of potential energy here, right? But no change in kinetic energy. Clear? Now let me ask you, what do you think will be the units of electric potential difference? So what is it going to be? If you look at this definition, then the unit should be electric potential difference. By this definition, work done is joules. Okay, and we know that the charge SI unit is Coulomb, so it should be joule per Coulomb, right? Joule per Coulomb. And another important thing is electric potential difference a scalar or a vector quantity? What do you guys think? That's right. The answer is it is a scalar quantity. So electric potential difference is a scalar quantity. So note down all these important things and the definition of electric potential difference. Now one thing you might have noticed is that when we were defining electric potential difference, we did not specify how we are moving the body, right, from 1 to 2. So we didn't specify the path. So it doesn't matter whether you move it in a straight line like this, or you say I want to move it in this kind of curved fashion, or some crazy path like this. If you go ahead and take some path like this, it doesn't matter, because the work done is independent of the path. The work done in moving this test charge okay, is independent of this path, and this is the work being done in an electric field. Okay, so this charge is moving in an electric field, right, and the work done is independent of the path. Now, why is the work done independent of the path? Because remember, electrostatic force, what type of force is it? A conservative or non-conservative force? That's right, electrostatic force is a conservative force. So electrostatic force is a conservative force. Note that down. Can you tell me any other force which is also conservative? That's right, gravitational force, it's conservative. Electrostatic force, it's conservative. So in such conservative forces, work done is independent of the path, and you can define the concept of gravitational potential energy, electrostatic potential energy, right? But if you consider non-conservative forces like friction, in friction, work done definitely depends on the path, and there's no concept of potential energy there. Clear? Now let me ask you a question, that what will be the work done if I move the this test charge from 1 to 2, right, and then let's say I bring it back to 1. What do you think is going to be the work done? That's right, the answer is 0. Why? Because it is a closed path. So when you move the body in a closed path and you bring it back to its initial position, the work done is 0. So let's note that down. Work done is equal to 0 in a closed path. And once again, why? Because we are considering a conservative force. We have talked about the concept of electric potential difference. Now let's talk about the concept of electric potential at a particular point. So let's say I want to define the electric potential at a point. How do I do that? Because the problem is that in physics, there's only the concept of electric potential difference. You need to do a difference, means you need to do a comparison. So how do I do that if I want to know the electric potential at a point? So once again, let's consider our original definition, that to get the electric potential difference, we need to move our test charge from point 1 to point 2, right? That's what we said. So you are bringing this tiny test charge from 1 to 2, and we had defined the electric potential difference like this, right? V2 minus V1 was the work done in moving from 1 to 2 divided by the charge, which is Q naught in this case, right? So this was the electric potential difference. Now if I want to know only V2, right, that means I want to make this V1 term 0, right? So what do we do? So then the scientist said that let's take this point 1 that we are bringing the test charge from to be very, very far away. And what do we call very, very far away as? That's right, it's at infinity. So why are they choosing infinity? Note here, because they said rather than taking 1, what we're going to do is V2 minus our point 1 is infinity. So V2 minus V infinity is the work done in moving the charge from infinity to this point 2 divided by the charge. And the advantage of doing this is, the scientist said that the potential, electric potential at infinity is 0, right? Because if you have a charge, creating an electric field, then it will have very little effect at a very far away distance, right? The electric field becomes 0 at infinity. So it seemed reasonable to say that, hey, let's consider, right, the electric potential, let's assume the electric potential at infinity to be 0. So we can say V infinity is considered to be 0. So now if I substitute V infinity as 0, so it basically becomes the V2 minus 0. So we are just left with the term V2 is the work done in moving the charge from infinity to this point 2, you can call it point A, point whatever you want, divided by the charge. Clear? So to define electric potential at a point, you consider moving the charge from very, very far away, from infinity to this point, and not in a hurry, very slowly, as I said, right, without changing its kinetic energy, and then you'll get the electric potential at this point. Clear? And once again, you can see the units will be joules per Coulomb, right? Electric potential has the same unit as potential difference, joules per Coulomb. So let's write that unit down also here, joules per Coulomb. Till now we were talking about the electric potential difference or the electric potential in a random electric field. Now let's talk about the electric potential created due to a point charge. Okay, so imagine we have a point charge here. Point means very tiny charge. Obviously I have drawn it with a big circle, otherwise you won't be able to see it. But imagine this is a very tiny charge, right? Tiny in size, right? And the charge is plus q. Okay, so this is our point charge over here. And we want to know the electric potential at point P, which is at a distance r from this charge. So we want to know the electric potential at this point. And there's a very important formula here which we are going to derive. The electric potential V, the symbol is V, is kq by r. Okay, so let's understand these symbols. Now what is this capital K? Do you guys remember? That's right, it is related to that permittivity. So remember, capital K was 1 by 4 pi epsilon, or if you are talking about vacuum, it was 1 by 4 pi epsilon naught, and K had that value 9 times 10 to the power 9. You guys remember it? So that is that same K which you have studied in Coulomb's law. Q is the magnitude of this charge, right? The charge here divided by this distance r. So this is the electric potential at this point. And again, what do we mean by potential? Just like we talked about the definition, it is the amount of work done in bringing a test charge from infinity. So let's say you have this test charge Q naught, you're bringing it from infinity to this point. So the amount of work done divided by the charge. And if you calculate that, it works out to this important formula, kq by r. This is the electric potential at this point P, kq by r. Now one important thing about this formula is that if our point charge is positive, we will get a positive electric potential difference. If the point charge is negative, then you'll put, for example, you'll put minus 5 Coulomb here, you'll get a negative electric potential. Okay, so this is important here, that if Q is positive, then the potential at this point P will be positive. If Q is negative, if you use a negative charge, then obviously you get a negative electric potential at this point P. Okay, now we'll see how do we derive this formula kq by r, and remember K is 1 by 4 pi epsilon. Let's look at the derivation of this formula for electric potential due to a point charge, right? And at a particular point we saw it was kq by r, that's the formula. Now we're going to derive it. So pick up your pen and paper and let's derive this together. So remember, we have a point charge over here, plus q, right, which I've labeled as capital Q, and we are moving this test charge from infinity to this point P. Okay, we are moving the test charge from infinity to P, and we know that the work done or the potential at P will be the work done divided by this test charge Q naught. Clear? So we know that electric potential difference Vp minus V at infinity, which we know is 0, so that's how it becomes the electric potential, is going to be the work done in moving from infinity to P divided by the test charge Q naught. Okay, makes sense? And we know that this V infinity is 0, so basically we know that electric potential Vp is going to be work done from infinity to P divided by Q naught. Now work done, it's very important to understand who is doing the work, right? Which force? So first let's look at this positive charge here, and we have another positive test charge here. So there is going to be an electrostatic force between these two guys, right? By Coulomb's law we know that there's going to be an electrostatic force, and what will be the direction of that electrostatic force? That's right, it is going to be repulsive because both charges are positive. So we clearly know that there is going to be a electrostatic force here in this direction, which I can say is F1. This is the electrostatic force repelling this charge. So basically we are having to do work, right? And we want to oppose this force in bringing it from infinity to P. And always we will match this, because remember, we don't want to increase the kinetic energy, we don't want to change the speed. So our external force will be in the opposite direction, right? Do you guys agree that we have to apply a force here, external force, which will oppose this repulsive electrostatic force in moving the test charge from infinity to P. And that is the external force here. Clear? So one thing we can clearly see that F external will be equal to F1. And what is the formula for electrostatic force? By Coulomb's law, we know it is KQ, the product of the charges, KQ times Q naught divided by the distance, and let's label the distance as x square. Okay. So let's say at a particular point, the charge is at a distance x from this, the test charge is at a distance x from our point charge. Okay. So this will be the magnitude of the external force, but we know that it is in the opposite direction. You have to apply a force in the opposite direction to bring it here. Clear? So now, how will you calculate the work done? Work done is simple, force times the displacement, but you can only do that when the force is constant. Here the force will vary according to the distance, because see, it's divided by x square. So again we have to use the help of our integration friend and integrate through tiny displacements. Okay. So note here, how do you calculate this work done from infinity to P? In bringing the test charge from infinity to P, it will be an integration of all these work done by the external force times tiny displacements, which we can take as dx. From where are you integrating from? Infinity to, let's say this distance is r. So we are bringing it from infinity to r. So our integration limits will be from infinity to r. Does this make sense? F external, and you can say dot tx over here, right? Is this clear? Now let's start substituting stuff here. Now let's start substituting these formulas for the external force, and let's put it in here. So we are doing an integration from infinity to r, right? Where x is from infinity to r, and the external force is equal to this electrostatic force kq q naught by x square times dx. But one important thing to note here is the external force is this way, and our displacement, if we consider this is the origin, x is measured that way, right? So if you consider these two as vectors, right? So F external, and if you're looking at the dx or dr as a vector over here, right? I'm using x here, others will be confusing with this r. So F external and dx, if you consider them as vectors, you can clearly see that x is in that direction, external force is in this direction, opposite. So these are clearly opposite to each other. So that means the angle between them is 180 degree. So I need to put a minus sign here, right? Work done will be negative, because if you consider displacement that way, force this way, work done is negative. Clear? So I put the minus sign and done the product. Make sense? Now it's simple, you just have to do integration. K, Q, Q naught, these are all constants. So let's get them out of this integration. They are free to come out. So K, Q, Q naught are celebrating outside. And then we are doing integration from infinity to r minus 1 by x squared dx. Now can you guys integrate this for me? Integration of, this is x to the power minus 2. Apply the integration formula, minus 2 plus 1. So that will give you a 1 by x, right? X to the power minus 1, and you have a negative sign there. So minus will, I think, cancel over there. So we are getting, so if we continue this, integration, we'll get k, q, q naught, and this integration will give me 1 by x. So it's a minus 1 by x, but the minus will cancel from r to infinity. Okay, now just substitute the limits, guys. So what do you get over there? K, q, q naught, 1 by r minus 1 by infinity, and 1 by infinity, all of you know, is what? 1 divided by a very large number. This is basically 0. So see, that's what we are left with. K, q, q naught by r. This is not the electric potential. This is the work done by our external force. For electric potential, remember the definition? The work done divided by q naught. So let's substitute this work done over here. So let's put it in over here, k, q, q naught by r, and this divided by q naught disappears, and see, we have got the final formula, kq by r. Congratulations, guys. we have got the electric potential formula. So this is the important formula that we have derived here using our concept of electrostatic force formula from Coulomb's law and just simple integration from infinity to P. Okay, so is this entire derivation clear? That the electric potential at a point P due to a test charge or due to a point charge, right, is equal to kq by r. And again, you know, if your q is negative, electric potential will be negative, this value will become negative. If it's positive, electric potential at this point P is positive, and always we are comparing it from infinity, right, bringing it from infinity to P. And that's the entire derivation here. Now that you know the concept of electric potential difference and electric potential, let's see how these concepts can help us to easily find the work done, right? So when we have been asked to find the work done in moving a charge, we have this +2, this is micro Coulomb charge from A to B, okay? So let's see how we can apply the concepts here. So first let's look at the question. We have this basketball here carrying a charge -5 microcoulomb. So don't think this as a large basketball that you're going to play with. This is again, let's assume it to be a tiny point charge. So I should have really drawn it as a dot, but you know, just to make it more visual, I've shown the ball here. So this is a point charge of 5 microcoulomb, and then we have got, you can consider this as your test charge that you're moving from A to B across this distance of 2 meters, and this is our charge. We are moving this from here to here +2 microcoulomb. And what is our task? Our task is to find the work done. Now normally, you know, work done we do by, you know, force times displacement, and if the force is variable we have to integrate. But the good news is that since we know the concept of electric potential difference, we don't need to do all those integrations, right? So what can we do here, guys? Let's apply the concept. We can say that if you're moving this charge from A to B, then the potential difference, we'll always take final minus initial, VB minus VA is going to be the work done by the external force divided by the charge Q. Make sense? So if I want to find the work done by the external force, I can just take it here. So I can just take the charge over there. So the work done is basically the potential difference VB minus VA times Q. That's it. And can we find VB and VA? Of course, we know the formula. We have just done its derivation. We know this formula, kq by r. So guys, use this formula and find VB, VA, substitute it here, multiply by Q, you're done. So no need to do any of those big integrations here. So we are going to apply the formula here. So let's find out first, let's find out VA. VA is going to be kq by r. So this is our Q, right? So capital Q is our point charge here, and this is like our test charge that we are moving, small q. So VA depends on this capital Q, which is going to be kq by r, and let's substitute the values there. So this is going to be equal to kq is -5 microcoulomb. So I said please use the sign. So -5 microcoulomb divided by the distance here is 1 meter, right? Distance from the point charge. So divided by 1. And potential at B is going to be how much? Again kq, and this is really RA, the distance from A. This is going to be RB. So K times the same -5 microcoulomb, and this time how much is the distance? This is 1 meter, that's 2 meters. So you have to do 1 plus 2, 3 meters, right? So this is 3 meters here. So there you go. That's your VB and VA we have got multiplied by Q. So we can easily get the work done. So let's substitute here. I'll bring the K outside and this -5 outside. So K times -5 microcoulomb, VB minus VA. So 1 by 3 minus 1 by 1, which means -1, divided and multiplied by Q. Q is +2 microcoulomb. There you go, guys. So micro, you know, means 10 to the power -6. So let's bring that out here. So, and K is 9 times 10 to the power 9. We're going to assume this is all in vacuum. So 9 times 10 to the power 9. You have a -5, 10 to the power -6 there. This is going to be 1 by 3 minus 1 is minus 2 by 3, right? Times 2 times 10 to the power minus 6. Okay, so go ahead and do all that calculations over here. So 3 and 9 will cancel. So we have a 3 over here. And what are we left with? So what are the numbers we are left with? The minus will cancel. So I'm getting a 5 and 2 will give me a 10. And there's a 3 and 2 will give me a 6. So I've got a 6 here. And what do we have? 10 to the power 9. And this 5 and 2 give me a 10 to the power 10. And 10 to the power minus 12. So please check my calculations. I think you should get 10 to the power minus 2. And finally, we have to find the work done. Work done, the units will be joules. So this is 10 to the power minus 2 joule. This is finally the work done by the external agent. So check, guys. So 3 times 2 is 6. And yeah, I think that looks okay. 10 to the power minus 6 times 10 to the power minus 2 joules. That's the answer. So did you see the advantage of the concept of electric potential difference? We didn't have to do any integration here because it was a variable force. It's not a constant force, right? But we didn't have to do all that, and we directly got the work done using electric potential difference. And work done is positive. It makes sense because this is a negative charge, this is a positive charge, so they're definitely going to attract each other. So if you're moving from A to B, right, in this direction, your force is also in this direction, right? Because you have to oppose this. This is an attractive force. They're going to attract each other. You have to push it away. So therefore, force and displacement are both in the same direction. We should definitely get positive work. Okay, so there you can see that's how we do this question. So till now we have talked about electric potential due to a point charge. But what if you have multiple point charges? Then how do we calculate the electric potential? So let's understand this with a simple example. Again, I've got my basketballs here. So you can see we have 4 basketballs. Let's number them 1, 2, 3 and 4. And let's say we are interested in finding the electric potential at the center of this square. You can see this is the square of side A. So I'm interested in finding the electric potential right at this center over here of the square. So right at this point, we want to know the electric potential V. Okay, at this point here in the center, let's label it O. So the good news is that electric potential is a scalar quantity. Remember, it's not a vector quantity. So we can just simply add it up. We don't have to do any vector addition. So we can simply say the electric potential at that center V is going to be electric potential due to charge 1. So V1 plus due to V2, right? Plus V3 plus V4. That's it. And how do you find the individual electric potential? Remember the formula? Electric potential was KQ by R. So again, assuming each of these as point charges, so go ahead and substitute the charge, and you need to find the distance of this point O from the charge. Now how do you do that? Just some simple mathematics here. This is A, this is each side is A, this is a square, and you know in a square or if you've forgotten that, diagonals bisect each other at right angles, so, and all these lengths are equal. So if I take this length to be R and this to be R, you can apply Pythagoras theorem. R square plus R square is A square. Can we do that, guys? So R square plus R square is equal to A square, or we can say here 2R square is A square. So if you take a square root, R is basically A by root 2. Can you guys see that? If you take a square root, R is A by root 2. That's it. You just have to substitute it there. So that's what we are going to do. So V is going to be equal to V1. V1 is what? There's a charge Q there. So KQ by R, or let's substitute the R at the end, because you can see the good news is the R is same throughout, right? The distance from the charge to the center is same. So I'm just going to keep it as KQ by R plus V2. There's another charge Q there. So KQ by R plus, now be careful here, this charge is minus Q. So don't substitute it as Q, use the sign, right? So this will become minus KQ by R, and the last one is plus Q, so plus KQ by R. So you can see that two of these terms will cancel each other, these guys cancel each other, And finally, we are left with 2kq by r. And if we substitute that r as a by root 2, I'm going to get 2kq a by root 2. So the root 2 goes on top, multiplied by root 2 divided by a. That's it. So it's like a principle of superposition of potentials, right? We have basically added up the potentials here, right? So we are just adding it up, simply adding, because it's a scalar quantity. So if you have multiple point charges like this, no issues, you can just add it up like this and get the net potential. So this you can say the overall or the net electric potential due to all these charges. Now let's try this interesting question. The question says find the points on line AB where electric potential is 0. So the question is telling us find the point. So maybe there's more than one point. Okay. And what do we have here? We have two charges plus 2q and minus q separated by a distance of 1 meter. So you need to tell me where are the points on this line AB, the line joining the two charges, where the electric potential is 0. So remember, what is the formula of electric potential due to point charges? The formula was V equal to kq by r. Now let's consider the first case of a point lying between the two charges, and let's see if the electric potential can be 0. So if I consider a point, let's say in the middle, can the electric potential be 0 there? Probably not, because you can see this charge is stronger than this charge. It is 2 times, right? So one is positive, one is negative, but it is double. So if I want the electric potential to be 0, then the point should be closer to this guy, right? Because this charge is smaller. So it's to have, to be able to cancel the larger charge, we need to consider the point closer to it. We have to give it some advantage, right? So let's consider this point here. Let's say point P, which is closer to minus q. Okay. So let's say this distance is x, and this distance will be what? It will become 1 minus x. So this distance, let me put the labels here. This distance is x. So this distance becomes 1 minus x, right? Now let's look at these two potentials. We want them to be 0. So basically we want that at point P, so Vp, which is equal to V1 plus V2 due to the two charges, and that we want to be 0. Now what is V1 plus V2? V1 due to this charge, let's apply the formula k times plus 2q divided by this distance. The distance is 1 minus x, plus, what do we have here? K times minus q divided by the distance, which is x. And that equals 0. That's it. I just have added up the two electric potentials. They are scalar quantities. We can add them up and equated it to 0. Now just you have to solve this equation. So if I take this to the other side, I'm getting k 2q by 1 minus x equals kq by x. And guys, as you can see, k will cancel, q will cancel. And if we cross multiply, we are getting 2x equal to 1 minus x. So 3x equal to 1. So that means x is 1 by 3 meters. So that means this point P is at one third of a meter here, 1 by 3 meters, and this will be 2 by 3 meters, right? Because this charge is stronger. So there you can see we have found the location of point P where electric potential is 0, and this was our case 1 for a point lying between the two charges. Now can you think of a point where the electric potential will be 0, which is a point on line AB outside, right? Not between the two charges, outside it. So will it be on the side of A or on the side of B? Think and tell me, right? So if you consider a point here, right, on this side, you can see 2q, it will be much closer to this plus 2q and much further away from minus q. So they can never cancel each other because this is a stronger charge, smaller distance, the electric potential will be even more, right? This is the weaker charge. So once again, the point has to be this side, closer to minus q. So let's try that out. So we are going to try case number 2 here. Case number 2, where we are going to consider our point here, let's say point here, q, where once again the potential is 0. Now where is this point? Once again, let's say it's at a distance of x from minus q. So this entire distance will basically become 1 plus x. And once again apply the concept that we discussed. The potential at point Q will be equal to V1 plus V2, and we know that it's going to be equal to 0. Now let's go ahead and substitute the formula. V1 is KQ, which is 2Q, by the distance R, which is 1 plus X here, right? This distance is, oh, this arrow doesn't look nice, so let me make it better. Yeah, that's the distance, 1 plus X. So let's put that in here, plus V2. This electric potential will be K times minus Q divided by X equal to 0. That's it. Now you just have to equate these guys. So we are going to get K2Q divided by 1 plus X, and on the other side we'll get KQ divided by X. Guys, let's cancel all this KQ stuff, will get cancelled. So I am finally getting, if I cross multiply, 2x equal to 1 plus x. 2x equals 1 plus x, right? So what are you guys getting? So if we subtract this, we are going to get 2x minus x, which will give me equal to 1 meter. That means this distance will also be 1 meter. So 1 meter from minus q, 2 meters from plus 2q. So that's our answer here. So see, the concept is simple, and you can see you can have electric potential 0 only when you have a positive and negative charge. If both charges were positive, if both were negative, then obviously you'll either get a totally positive electric potential difference, potential, or a negative electric potential, right? But when you have a plus q minus q, you can have these points where the electric potential is equal to 0. Now let's look at how do we calculate electric potential due to a uniformly charged ring. So let's say we have a ring like this carrying a total charge of plus q, and the charge is uniformly distributed about this ring. Okay, so let's say it's a metallic ring having the uniformly charged positive charge distributed all across the ring like this. And I want to find the electric potential at this point P. Okay, which is at a distance x from, let's say, the center of the ring, and the ring has a radius of a. So how do you find the electric potential here? Can we go ahead and say that the electric potential at point P is going to be kq, right? I take the entire charge q divided by the distance x, right, the distance. So can we say that V is kq by x? Can we apply a concept like, you know, the center of mass, where we assume the entire charge is here at the center of this ring, and so we can use that distance x? The answer is no, right? We can't do this, because what is the problem here? The charge is actually not at a distance x from P, right? The charge is not at the center, it's all around here, and if you want to know the distance, you have to consider this distance. Let's say I consider some charge here, I need to consider this distance, right? From P to this point, or let's say a point here, from here to P. So this is my real distance r. I cannot use kq by x. So this is definitely not going to work. So what do we do here? Now since this charge is uniformly distributed, it's not a point charge. So we are going to break it into tiny parts, right? Tiny point charges. So let's do that. So let's say we have a tiny point charge over here, right? Charge of dq. So we're going to break the ring into tiny charges dq, and so I can say the potential at this point P dV, the electric potential, is going to be equal to k times dq divided by this distance r, right, from dq to P. So this is absolutely fine, right, because we've considered a tiny point charge here. Now if I want to know the total potential here, I just have to add up the potentials due to all these tiny charges, right? Electric potential, we can simply add it up. So what do? The total potential V is going to be integration of this k dq by r across this entire ring here. And you'll notice something very interesting, that no matter what point charge you take, this dq or this dq or a dq over here, anywhere you take the dq, can you see that the distance r will be the same? because imagine it's like a cone, okay? So from the vertex of the cone to any point on the base, the circular base of the cone, the distance r is going to be the same, right? What in maths we call as the slant height, right? So this is basically the slant height of the cone. You can imagine this. So r is like your slant height and it's going to remain constant. And that is very helpful for us because in the integration we can bring it out, right? K is a constant, r is also not variable, it's a constant here. So for all these tiny charges, these guys come out. So K by R comes out and you're really integrating across the entire ring. So 0 to Q, integration of dq, this is going to be the electric potential. And here what do we get? So when you integrate dq, right, you'll get Q from 0 to Q. So we are getting kq divided by R. Okay. But R is a quantity that we introduced. We really wanted it in terms of x and this radius a. So once again, Mr. Pythagoras is going to help us because you know that this is a right angle triangle where r square is equal to a square plus x square. We can write that, right? R square is a square plus x square. Or you can say r is square root of this. So that's it. We are going to apply that here and we are going to get kq by square root of a square plus x square. There you go. That's our electric potential, right? So electric potential due to a uniformly charged ring of radius a at a distance x from the center. Now if I ask you, what is the electric potential at the center point, right? What will be the electric potential right at the center of the ring? Very simple, because for that what will you say? X is equal to 0. You've come right to the center. So we can say V at the center, the potential difference, electric potential at the center is going to be kq divided by square root of a square plus 0, right? Distance x is 0. So that's basically square root of a square, which is nothing but a. So I can write that as kq by a. So there you go. We've got some nice two important formulas for at an arbitrary distance x and at the center of the ring, it's kq by a for a uniformly charged ring of radius a. Now let's talk about electric potential due to a dipole. Do you guys remember what is a dipole? That's right. Two equal and opposite charges separated by a very small distance. Of course, here I've shown the distance to be large, otherwise the diagram is going to be really, really tiny. Okay, so there you can see equal and opposite charges plus q and minus q separated by this distance 2a. So here O is the center of the dipole. And let's say we are interested at the and let's say we are interested in the electric potential at a distance x. And remember, we measure the distance from the center of the dipole. So we are interested at a point over here, let's say a point P. So I want to find the electric potential at P due to this dipole. So what is it going to be? So we can say that the electric potential V will be equal to the potential due to the two charges V1 plus V2. Now once again, these are tiny point charges, so we can use that formula, right? We can use the electric potential formula V equal to kq by R. Okay, so let's go ahead and do it, guys. V1 and V2. So here V1 is going to be, let's take the positive charge as charge number 1 and the negative one as charge number 2. So V1 is going to be k and small q. And what is the distance here from the positive charge to the point P? That's right, it's going to be x minus a, right? So this distance, this part is x minus a. So let's put that here. This is going to be x minus a. And what is the potential due to the negative charge? V2. V2 is going to be kq divided by this total distance, which is going to be x plus a. So you're going to add up this a as well, right? So divided by x plus a. That's it. We just need to combine these two guys to get the net electric potential at point P. Simple. So you just have to do some maths here. So let's go ahead and let me do it here. So V is going to be equal to V1 plus V2, which is kq divided by x minus a. And one mistake I did, this is a minus q. There I didn't put the minus sign. We must put that here. So this is going to be a minus q. Okay, because that's going to give me a negative potential. So minus kq by x plus a, right? So go ahead and take the LCM over here. So if you go ahead and take the LCM, it's going to be x minus a times x plus a, and here we can take kq common times x plus a minus of x minus a. So that's it. Go ahead and simplify. So the denominator you can see is clearly going to be x square minus a square. So in the denominator we have x square minus a square. In the numerator we have kq, and this x and x will cancel each other. So a minus of minus a is plus a, so times 2a. There you go. And remember, what is this q times 2a? Charge times the distance, charge of any charge of the dipole times the distance between the two charges, which is 2a. That's right, it is called dipole moment, and the symbol was P. So we are going to use that here and say the final electric potential is going to be K times the dipole moment P divided by x square minus a square. There you go. That is the net electric potential here. So that's going to be our potential along the axis of the dipole at a distance x from it. Now you know that dipole, we said, is two equal and opposite charges separated by a very small distance. So typically we know that this a is much smaller than x, right? The distance x is typically larger. So if we say that if a is much smaller than x, that means we can ignore it. So a square will be even smaller than x square. So then the formula becomes kp divided by, we are going to ignore this a square term, kp by x square. That is the electric potential on the axis of dipole. And it looks, that x square reminds you of electric field, but don't be confused. This is a dipole, and this is the electric potential due to the dipole is kp by x square. That's the final formula. So if you can neglect the size of the dipole, use this one. If you can't neglect it, then we have got the general formula here as well. So you can use that too. Okay. So we have calculated electric potential on the axis of a dipole where it is at we are considering a point at a distance x from the center of the dipole. Now let's see if we can calculate the electric potential on the perpendicular bisector, right, of the dipole. So let's say this is our perpendicular bisector, right, of the dipole, and we are interested in electric potential at some arbitrary point here, P on the perpendicular bisector, at a distance once again x from the center of the dipole. So can you guys pause the video here and tell me what will be the electric potential there? So once again we are going to use the same concept, that the electric potential or the net potential is going to be the electric potential due to the two charges V1 plus V2. Let's say positive charge is 1 and the negative charge is 2. Okay, we want to find the V net over here at P. So I'm going to use the same formula, KQ divided by, this is the distance here, R, right? That's the distance R. So KQ by R, and this is going to be plus K, and this is minus Q over here, divided by R. Now note, because of this symmetry, can you see? This is a isosceles triangle, right? Both the sides are equal because you can see this is the perpendicular bisector. So these two distances R will be equal. And if they are equal, can you see what are we going to get here? KQ by R minus KQ by R, and the electric potential at any point on this perpendicular bisector is going to be 0, and this we can say that was the last time we found the electric potential on the axis. What is this called? This is called the equatorial position, right? So this is called the equatorial position. So any point on the equatorial position of the dipole or the perpendicular bisector is going to be equal to 0. Why? Again, think practically why? Because both are equal and opposite charges, right? And the distances are same. So we don't have to do any calculations here. There you can see it is 0. By the way, this distance R is square root of x square plus a square if you want to find that out. But we know the distances are same, so it's going to cancel. And there you go. The electric potential is simply 0. We have looked at the electric potential on the axis of the dipole and on the perpendicular bisector. But what if we consider any random point? How do you find the electric potential there? So we can use the same trick that we had used earlier to find the electric field due to a dipole. Do you guys remember? So if you look at any random point, right, again considering from the center of the dipole. So if I consider any random point here P, or let's call it point A over here, we have got A also, so let me use some other variable, let's say B. If you consider any random point B here, and this angle that this point makes, this line makes with the dipole is theta, and this distance from the center is x. So this reminds you of, those kind of polar coordinates x comma theta, and we are interested in finding the electric potential at this point P. So how do we do that? So one simple trick we are going to use is, we are going to break our dipole moment, because remember our dipole moment is here, dipole moment P, we are going to break it into two components, one along this line, right, and one perpendicular to it. So I'm going to break the dipole moment into two parts, this part and this part. Now you can see this dipole moment is P over here. So what is this component going to be? This is like dropping it on the base. So that's right, this is going to be P cos theta. So the dipole moment along this will be P cos theta, and along this it's going to be P sin theta. Do you guys agree? So now, since we have broken up our dipole, it's like the original dipole no longer exists. You've broken it down into two parts, P cos theta, P sin theta. So now we can ignore this, and now we're going to find the electric potential at this point as a sum of these two, right? Sum of the two electric potentials. So once again, let's do that. So the V net, the net electric potential at B is going to be V1 plus V2, or I can say okay, let me write that first, V1 plus V2. Now electric potential due to this P cos theta dipole, this point B is on the axis of the dipole. So I can say V1 is like my electric potential on the axis of the dipole. And for 2, if you consider this P sin theta, this is on the perpendicular bisector. B is on the perpendicular bisector of the dipole, because note that the dipole is here, right? So this entire part is the dipole, right? So this is like on the perpendicular bisector of the dipole, and this is along the axis of the dipole. So this is going to be an equatorial position. So that's it. We are just going to add the two. Now what is the potential on the axis of the dipole? What is the formula? Do you guys remember? So let's go back and check here. So the potential on the axis of the dipole, again assuming that the dipole length is very small, was Kp by x square. So let's apply this formula here. So we are going to apply this formula and say the potential along the dipole, along the axis of the dipole, is Kp by x square. But is this expression completely correct? No, because P is the original dipole. We are looking at the P cos theta, right? We have forgotten about the original. We have broken it down. So I must replace dipole P, the dipole moment P, with P cos theta. So this is going to be P cos theta. So there you go, that's fine now. And the dipole moment due to the equatorial position, remember, it was very simple, it's always 0. So we are going to put that to be 0 over here. So there you can see the net electric potential at any random point x comma theta is going to be Kp cos theta by x square. There you go. And one very important thing to remember, this angle theta is the angle between the dipole moment. Dipole moment is always from negative to positive, right? Remember, from negative to positive, and the angle made with this point B. So you always consider in this direction. So suppose your point B was here, then the theta would be a larger angle, right? An obtuse angle. You will not consider this angle. So always take it in the direction of the dipole moment and the angle made with the point P. And there you get the formula Kp cos theta by x square. So simple. So friends, let's summarize the formulas that we have learned to calculate the electric potential due to an electric dipole. What are the formulas? On the axis of the dipole, remember, it is Kp by x square, where once again we are ignoring the length of the dipole there, and P is your dipole moment, which is basically, how is it calculated? The dipole moment is any one charge times the length of the dipole. So Q times 2a, and remember, dipole moment direction is always from negative to positive, right? So dipole moment direction is this way. Okay, so that's the potential on the axis of the dipole. So we have done the formula for the axis of the dipole. Then we have done on the perpendicular bisector, which you can also call as the equatorial position, and that has a very easy answer. It's always going to be 0. And then we did for any random point, right? Any random point we considered, once again taken at an angle theta with the angle it makes with the dipole moment. So at any random point x comma theta, it is kp cos theta by x square. Clear? And you guys can check this formula. So for the axis of the dipole, what will be the angle? The angle theta is going to be 0, right? For the axis of the dipole, angle theta is going to be equal to 0. So there cos theta is equal to cos of 0 is 1. So there you go. If you put cos theta equal to 1, see, you get the first formula, kp by x square. And when you take a perpendicular bisector, what is the angle it makes with the dipole? Theta is going to be equal to 90 degrees. And what is cos of 90, guys? Cos theta then will be 0. So if you apply this general formula, see, you will get the potential equal to 0. So actually you can just learn this formula and you will get both of these two special cases as well. So those were the formulas for electric potential due to a electric dipole. And now here's a homework question for you to try. So let's take a look at our question. Find the electric potential at the point of intersection of the diagonals of the rectangle shown below. So there you can see a rectangle here having my 4 favorite basketballs. This basketball has a charge of +1. This MC is millicoulomb, right? This is also +1 millicoulomb. This is -1 millicoulomb and -1 millicoulomb. And the dimensions of the rectangle are given to you. You need to find the electric potential at the point of intersection of the diagonals, right? So go ahead and draw out this diagram and find me the electric potential over here at this point P. So that's the homework question for you. Go ahead and find the electric potential here and do let me know your answers by putting it in the comments below. I look forward to reading your answers and I promise to reply to them. So go ahead and try this out and put your answer in the comments below. Friends, I hope you liked this video and learned from it. And do check out the full courses on our website manochaacademy.com and our Android app Manocha Academy. All the links are given below. We have courses on physics, chemistry, biology, maths, coding and artificial intelligence. And we have our new IIT and NEET Foundation courses for classes 9 and 10. So do check it out. Links are given below. Now what do you get in our courses? You're going to get live classes, concept videos, quizzes, questions, mock tests and revision notes. So they will be perfect for your exam preparation. So do share it out with all your friends. And if you like this video, do hit the like button right now. And if you haven't subscribed to our YouTube channel, come on, what are you waiting for? Smash that subscribe button right now and click on the notification bell so that you don't miss out on any of our videos. Hitting the subscribe button costs you nothing, but it motivates us to make more nice videos for you. So stay connected with Manocha Academy and just keep learning.